On the stochastic processes playlist, we now move on to look at Brownian motions. So in the next set of videos, I'll be looking at Brownian motion. And the first video about it is the definition of Brownian motion. Okay, so first, a historical background. Brownian motion, of course, was first observed by Robert Brown in 1827 while studying pollen particles suspended in water. Right. Later, Albert Einstein in 1905 provided a theoretical explanation, and then Norbert Wiener developed the mathematical formulation known as the Wiener process. That is why sometimes Brownian motion is also known as the Wiener process. So the intuitive definition, of course, goes something like this. That Brownian motion describes the random and continuous movement of particles suspended in a fluid. So you have random and continuous movement of particles. So, and we have key characteristics like that. The motion is random and unpredictable, and then no fixed direction caused by collisions with molecules of the surrounding medium. So if you are to try to draw a picture, a possible picture of Brownian motion, it will look like a kind of you know, something just moving all over the place without a particular direction, right? So imagine you have a polling at this point, and then let's even imagine you have a container, a bowl like that, and then so to talk about the motion of this particular polling, so imagine that it now goes, it goes just goes all over the place, just keeps going, you know, and after some time, it's just all that. So imagine a kind of mathematics that studies this kind of motion that is random and continuous. That is what Brownian motion is all about. So, um, so, like we said, the key characteristic of binary motion include the fact that motion is random and unpredictable. There's no fixed direction, and it is caused by collisions with molecules of the surrounding medium. So, then we talk about the formal mathematical definition of Brownian motion. So, first of all, we have a stochastic process, which is the collection of all B of t for t greater than or equal to 0. It's called Brownian motion if, first of all, we have an initial condition. The motion at time 0, the process at time 0 is equal to 0. That's the initial condition. Then we have independent increments, meaning that the Brownian motion at time t2 minus Brownian motion at time t1 is independent of past values, right? So whatever we have between t2 and t1, it does not depend on values before t1. And then we have stationary increments, meaning that the stochastic process, the Brownian motion at time t plus s minus b of s is normally distributed with mean 0 and variance t, like that. Then it's also normally distributed. We also have normally distributed increments, meaning that the Brownian motion at time t minus Brownian motion at time s is normally distributed with average with mean 0 and variance t minus s, like that. Of course, you can already imagine here that the variance is t plus s minus s. That's why you have t. And here you have t minus s, like this. So, and then you have continuous parts, meaning that b of t, the Brownian motion at any point in time, is continuous in time. So, and then we go ahead to talk about mean and variance. So for standard Brownian motion, we already can see from the distribution, right? From the normal distribution that the mean is 0. That is why the expected value of the Brownian motion at any time t is equal to 0. And then the variance is t, variance of b comma t is also t, as we can see from here. And then we move on to consider connection to random walk. We had considered random walk previously. So we see that Brownian motion can be viewed rather as a limit of a random walk. So as a random walk continues endlessly. So if you take it as n approaches, as the number of steps approaches infinity, then we get the Brownian motion. So you can say Brownian motion is the limit of a random walk, if you like. So that means that b of t is limit as n goes to infinity for the summation from I equals 1 to n of xi over square root of n, where xi are independent random variables, like that. So example 1 now, we have this that we want to find the distribution of B3. Okay, so from the definition, right, we know that Brownian motion is normally distributed with mean 0 and variance t. Thus, we can say that Brownian motion of 3 is normally distributed with mean 0 and variance 3. So variance is the time basically. So the mean is 0 and the variance is 3. So that tells us about the distribution. So it is normally distributed with mean 0 and variance 3. And when we go to example 2, we have this that for example 2 now, we want to find the probability that the Brownian motion at time 2 is less than or equal to 1. So the solution then, since Brownian motion at 2 is normally distributed with mean 0 and variance 2, then we can standardize that to say z is 1 over root 2. Of course, uh that's something like the z is x minus mu, right? So that's x here is 1 and mu is 0. So that's 1 minus 0 all over standard deviation, all over square root of the variance, which is square root of 2. And that is approximately 0.070. That's the standard value. So thus, now we have the probability that b of 2 is less than or equal to 1 is then probability that z is less than or equal to 0.707. And of course, if we use if we use the table, four-figure table, we can get that to be, I think, normal distribution table, I believe, and that's approximately 0.76 in that case. So the probability that b of 2 is less than or equal to 1 is 0.76 or 76%. So the 76 out of 100 chances that the Brownian motion at time 2 is less than or equal to 1. So we can have a Python simulation for this. Okay. So Python simulation of Brownian motions. So here we declare the time to be 1. N is 1000 steps. Then dt is t over n. And then we dB now is now we have square root of dt, square root of t over n now. Np dot random. We do all of that and then we get something like this. So we have the simulated Brownian motion like this. So this time here and then the Brownian motion right here. Okay. So for example 3 then, we have to find the distribution of B5 minus B2. And from the characteristics of Brownian motion we already saw, right? To find the distribution of B5 minus B2, using the properties, we know that B5, we already know that BT minus BS is normally distributed with mean 0 and variance T minus S, right? That's 5 minus 2, and that means B5 minus B2 is normally distributed with mean 0 and variance 3. So here the mean is 0 and the variance is 3. So talking about applications of Brownian motion, then we see that we can apply Brownian motion in physics. Of course, that's there we talk about particle diffusion, and then in finance we talk about stock price modeling. In biology we talk about molecular movement. In engineering we talk about modeling noise modeling. So, and then we have in summary that Brownian motion is a continuous time stochastic process. It has independent and normally distributed increments, and variance grows linearly with time, and it models random continuous motion. And that leads us to the practice problems as usual. So we have to show that for Brownian motion B of t, the expected value of B of t is 0, and then prove that variance of B of t is equal to t. So you want to check all of that up. So I didn't talk about it, but we are just talking about the definition. Probably as we go on, we'll see all this. Then find the distribution of B4. Of course, the distribution of B4 will simply be, so B4 is normally distributed with mean 0 and variance 4. That's all. Then we want to compute probability that B1 is less than or equal to 2. So we follow what we did the other time, that'll be okay. I guess I want, okay. I mean, let me just keep going and see if I'll need to come back to do this later. So we need to compute probability the Brownian motion at time 1 is less than or equal to 2. I want to find probability that Brownian motion at 3 is greater than 0. I want to determine the distribution of B6 minus B2. Then compute expectation of B5 minus B2. Then find the variance of I think, of course, the expectation would always be 0, right? So I think even this will be 0. Find the variance of B5 minus B2. I think we saw that before. Then, of course, the variance will be 5 minus 2, 3, because it's a change in time, right? So show that the increments of Brownian motion are independent. We saw that before. Verify this. So it's more or less like showing the same thing. Then compute this, find the covariance B2, B5. We are going to see all this as we go on later. Then show that covariance of BS, BT is minimum of ST. We are going to see all that too. Then find the distribution of 2B3. 2B3. Then compute probability that the absolute value of B1 is less than or equal to 1. That simply means that minus 1 lies between, I mean, B1 lies between minus 1 and 1, like that. Then we then have to find the distribution of B3 plus B5. Then compute expectation of B3 multiplied by B5. That should all be zero, I believe, because expectation of BT at any point is zero. So show that Brownian motion has continuous parts and explain why Brownian motion is nowhere differentiable. Then let X be B2 plus B5. Find the mean of X. Of course, the mean of B2 is zero. The mean of B4 is zero. So mean of X is zero. The variance will be 2 plus 4, 6, and that's it. So yeah, that's what this is about. So if I'll take any of the questions, I feel that I should take question 15. We want to show that the probability of the Brownian motion at 1, absolute value of Brownian motion at 1 is less than or equal to 1. So let's see how far I can go with that. So we want to compute the probability that the absolute value of the Brownian motion at 1 is less than or equal to 1. Okay, so that's like saying the probability that minus 1 is less than b1, and that is, I mean, less than or equal to b1, and that's less than or equal to 1. Okay, so from what we did the other time, we want to get standardized, right? So we want to standardize like we did already. So here it means that z now is going to be, would usually be x minus mu all over all over square root of the variance. The square root of variance, well, square root of sigma squared. And from what we have here, right, from this whole thing, right, we know that B1 will be normally distributed with mean 0 and variance 1, right? That the time is the variance. So usually B of t is normally distributed with mean 0 and variance t. That's what that means. So if we have B1, then it means that the mean, so it means that from here now, mu is equal to 0, this now, and then sigma squared is equal to 1. That's this now. Then, of course, talking about the x will be minus 1 and 1. So we have, so we can standardize all that. So we then have, we have z1. Z1 is, um, yeah, Z1 will be x1 minus mu all over square root of sigma squared. Okay, that'll be, so I like to take x1 as this is x1 and this is the first x is x1, this is x2. So that means we have minus 1 minus mu, which is which is 1, all over square root of sigma squared, which is 1. So it means that z1 is equal to minus 2, yeah, minus 2 over 1, which is simply minus 2. So we know that Z1 is minus 2. We keep that. Then we move on to Z2. So Z2 is x2 minus mu all over square root of sigma squared. So x2, like we know, is 1, you know. So we have 1, all right, 1 minus mu, which is 1 also. Mu is, oh, okay. I think something is wrong somewhere. Mu is 0. Yeah, sorry. Mu is 0. Okay. So this should just be, so since mu is 0, right? We have minus 1 over 1. Okay. And then this is, Z1 is minus 1. So then x2 is 1 minus 0 all over square root of 1. So z2 is 1 over 1. And z2 then is equal to 1 still. So in essence, the probability that the absolute value of b of 1 is less than or equal to 1 is the same thing as that probability that z1, all right, is less than or equal to less than or equal to um what should I represent b of 1 with now? It can now be, should I say z now? It's less than or equal to z, and then that's less than or equal to z2. So that means that we have probability minus 1 is less than or equal to z, is less than or equal to 1. like that. So we need to figure this out. So let me see. I don't have a table to do this, but let me just use Google. So I just have probability that -1 is less than or equal to Z is less than or equal to 1. So let's see if we can find that. Um, Okay, I think that's possible. So the probability that P is -1 less than or equal to Z less than or equal to 1 is for a standard normal distribution is approximately 0.6827 or 68.27%. Yeah, okay, that definitely works. So that's 0.6827. So if you have a table, you can check it. 0.6827, 0.6827. Okay, so in that case, now we can then conclude. Therefore, probability that the Brownian motion at 1 is less than or equal to 1, right? Is equal to 0.6827. And if you like, that's like 68.27%. So there's a 68.27% possibility that the Brownian motion at time 1 is less than or equal to 1. So that's what I think that should look like. And with this, we come to the end of this interesting video, which is an opener for the idea of Brownian motion, talking about the definition of Brownian motion. So we continue to deepen our understanding of Brownian motion in subsequent videos. Don't forget to try your hands on the questions. So here you have 1 to 5, you have 6 to 10, you have, okay, I mean, up to 10, then now you have up to 15, then you have up to 20. Okay, so with all of this in place, so try your hands on this and let's see how well you have an understanding of what's happening here. So watch out for subsequent videos to deepen your understanding of this idea further. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. So you can, so that gives you special privileges like getting to see some videos first or seeing some videos exclusively. We can also hang out together to discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.